Okay, welcome back. All right, I know you guys are getting tired. Yep. Okay, so maybe I want to go through some of the tricks in some of the linear that machine learning do offer in terms of linear model, because I guess in statistical like a process, like a statistical method, it doesn't allow you to do much apart from just solving the OLS, or ordinary least squared, exactly. But in machine learning, it's because it's kind of like a fuzzy ways of fitting your model. So it does provide some tricks that you maybe consider in the future. One of this is called RANSAC. It's called the random sample consensus. So essentially, it's the same thing as the regression model, but then it's only fit to the subset of data. I guess if you want to do something like this, it probably means that you want to avoid the outliers. So instead of getting rid of your data, like you might not want to get rid of your data, but you kind of experiment with how your model is actually taking the portion of your data to include in your model building. Okay, as you will see from the example. Okay, it's actually it's quite easy to use, but it can be you kind of have to beware of how much you are using your data, which can be good or bad depending. Okay, so let me show you how to use it real quick. Okay, so c2.ipynb. You can follow me from the example. Okay, so first I want to import everything's in here. I don't need this one. Oh, actually open too many things. This one. Okay, right here. Utility functions first, and then there you go, all the libraries. Okay, so here I'm going to use the RANSAC regressor right here in addition to the linear regressions. Okay, so essentially we can use RANSAC regressor for any type of regressions, but I'm just going to show you for the linear regressions only. But you can apply this type of techniques of data exclusion to any type of regression models. Okay, and here you're going to start seeing something like this from now on, because the process is the same, right? You're loading the data, you're extracting the data, and then you're splitting the data. So I've include everything in one box. Okay, so that you can just run it and get all the things you need. Okay. All right. So and as you can start seeing, like when like in my example, I normally want to try like different parameters, and I don't want to type a lot of things. I don't want to keep changing the parameter. So I want to type everything in here so that, and then I can just loop everything, like automatically run all the models. So the way that I do is actually I separate things by experiment. So like experiment 1, I want to do, there's the parameter called residual threshold, and you will see what it does. Okay, I want to change this residual threshold from 1 to 5 to 10. Okay, and if I were to do this, I want to run things like I want to run all the experiments at once, right? So I gotta loop it in some way. Okay, so let me show you this one. Okay, if I were to set my I guess my experiments like this, when I want to loop something, I can just loop through this parameter sets right here. So let me show you. If I were to do for, right, I want to do name and values, right, in param set dot item. Okay, let me show you the way that I do here. Okay, if I were to write it like this is like a loop through the items in my dictionary, right? So in my dictionary, I have the key and the value. Okay. So if I were to print first, if I were to print name, you can see that it's printing the key, which is ex1, 2, and 3, and so on, right? And if I were to print values, it will print the parameter that I set. Okay, so that's how I do it. I specify all the things that I want to do in kind of like the big dictionary, and inside there's another dictionary with the name and the value, which is the parameter itself. Okay, so let me just show you if I were to use one of this, right? So I I would use this value to construct my model. Okay? And my model is called ransack regressor. Actually, this is not even my model, but this is the wrapper from my model. It's using ransack regressors, right? In my ransack regressors, I want to type in the value. Like if I were to type in manually, I would have to do this. Residual threshold equal 1, or 5 or 10. If I were to do it manually, I would have to do this. But I don't want to do this, right? Because I already have the value that's changing in here. So I want to do this automatically using the variable values. So essentially, I want to turn this thing into something that's more automated. So you can do something like this. And then I change into value. Okay? But this one is not exactly the same as the one above, because this one is actually not dictionary. Like my value is a dictionary, but this part is actually not dictionary. It's actually kind of like the keyword arguments, right? So there is a nice trick that I always use in my code, which is to kind of changing the dictionary into the keyword argument. So that's what it is. So I guess you kind of have to wrap your mind around it and kind of convince yourself that the above line and the second line kind of do the same thing. But the line below is actually automated in terms of the value is actually changing every time I looped into it here. Okay, so that's the weird, the strangely looking double star in my code. So that I want to expand the value into it. Okay, but then there is actually other values that I don't want to care. Like there are more things that I might want to fix in all the experiments. And I can type it in here. For example, I can do estimator, right? Equal. So the estimator is actually your regression model. And here we already learned we only learn one thing, which is linear regression model. So I want to do linear regressions. But notice that in here, I need to do this parenthesis right here, because the estimator is not it's accepting not the class definition. You have to input the object instance into it, and when I say object instance, it has to have this parenthesis right here. So there's a difference between when you just type linear regression without the parenthesis and with the parenthesis. You want the one with the parenthesis because it's the object instance, not the class definition. Okay? And then the rest is something that I don't want to change between experiments. For example, max trial. Okay? So these are some of the details that if you are interested, you can look into the documentation on what it's doing. And I want to do min samples. Okay. 50. Okay, and I can do loss equal absolute error. So that's something that I just checked into my into the documentation. Okay, maybe I can just copy it because I don't want to make error. Okay. Okay, something like that. If I were to format my cell, then I get something like this, exactly as I show you in my example. Okay, so that's what it is. So I'm also gonna comment this out because this one is not automated, right? So so the only thing that I change in here is the residual threshold, which you will see what it's doing, right? So next, what I want to do is I want to go through the I guess the process of building the model and fitting and doing the evaluation. So I want to make this one equal to a variable called RC, I guess ransack regressors. And I want to do rc.fit, right? I want to fit all these models with my train data, so x train and y train. Okay. And after I fit, I want to calculate the prediction so that I can do the residual plots and MST and R squared. So I do y train predict, right, equal to rc.predict. And then I give them x train okay? And then y test predict equal rc.predict and then x test, okay? And then I want to store all the results. So this one is a bit kind of complicated, but essentially what I want is that I want to like show you the table of things to use. So then the things that show you the table of things that I use, right? So I stored it into a collection. This one is called tuple. Okay, let me just copy that because it's kind of long. So as you can see that, where's the results? I need to do results in here. Oh, actually, this one is my function. It's not even, I need to run it, right? Where is my store results? I missed something in here. Where is it? Oh, yeah, wait. I should have it here. Oh, right here. Okay, sorry. So store result is a function that I kind of like a helper function that I use to store things. So this one is something that I implemented on my own. So no need to worry about it. Okay, so just to make sure that I can print things to you so that you can see, you can compare things. Okay, so this one maybe don't need to care too much about it. Okay, but the things that I want to show you is that I want to plot. So here, I want to plot the regressions with different values. Okay, so let me do that. It's almost like I copy everything already. Okay, fine, I just copy everything. Okay, so let me just run it, and I think you already run it too, right? Okay, so what you're seeing, maybe you can use this one first. Okay. So what you're seeing is that the blue lot is the entire data, but then our fitting algorithm actually using the orange or the pink dot as the training data. So let me tell you again. So the training data is the blue dot. So that's the thing that we fit into the model. But the model is actually only choose the data that along its the mean value. So it's actually ignoring all the blue dots when you are building the regression model. Okay, so it's only picking the pink value to fit it, and that's something that you can use if you want to experiment with, how is your model perform if you only pick the certain things that lies in your during the mean values. Okay, but then you can also control how much data you want to include in your model building. For example, if you, increase the number of the parameter called, I remember the name, it's called the residual threshold, then you can start to include more value. And as you can see that it's going to influence how you fit your linear lines in here, okay? Or you can even include a lot of value, okay? But again, if you were to do this, then you can kind of see that if you start to increase your, your threshold, if you start to reduce your threshold too much, then your R square might suffer. So it's kind of interesting because it's kind of if it's 1, then it's doing roughly okay. But if you increase it, it actually reduces and then it comes back again. But overall, this method actually helps you make a model that's more resilient to outlier, essentially, without having to actually delete your data. Like, because I guess for data scientists, like deleting data is actually quite scary. Like, we don't want to delete anything, but we want the model to actually ignore the outlier. So that's kind of a nice trick that I think might become useful in the future. Like, if you were to automate this process, right? For example, if you write a software that performs linear regression to the new data that comes in, and you use ransack regressors, and then you set the threshold to be quite low, so that means that if the outlier come, your model is actually not affected. So I think that's kind of nice in terms of like automation and writing the logic to avoid outliers. Okay, so that's ransack regressors. Okay. In terms of trying to kind of like change your model or make it more robust to change it to outlier, there's actually another thing that you can use. It's called regularized regressions. And it's, I guess the overall theme of this is actually to reduce complexity and overfitting. So again, if your data is noisy, you have a lot of outlier, your fitting might be that might fluctuate. Like your weights might goes ups and down a lot, and maybe, I guess it's less robust to noise. I guess that's what I want to say. Okay, so you can do regularized regression. There's 3 ways to do it. So the first one is called rich regressions, lasso, and elastic net. Okay, so it's a lot of names in here, but essentially all of this, what it's doing is different ways of making sure that your weight is not too high. Okay, so that's what it is. Okay, so some equation just to explain the difference. So the first one is called rich regressions. If you were to remember, recall when we're talking about a perceptron, and during the training, in perceptron, it's actually trying to minimize the cost function, right? J right here, and J can be defined by multiple ways. In terms of regression, we define it by this terms right here. This is the error, essentially. It's difference between the prediction and the real value. So that's the error. So makes sense, right? When you're trying to do linear regression, you want to minimize the error. So that's your objective function. But then if you're doing the rich regression, then you actually have another term called the regularization terms. So this term is actually scaled with the value of your weights. So what it's doing is that if you are reducing the error, that's good, but you want to reduce the error in such a way that your weight does not blow up too high. Because when your weight goes up, that means your model is very, very sensitive to the input data, and you don't want that to happen. So you kind of try to tame the value of your weight by including this term into your cost function. Okay? And you just go through the normal optimization process as usual in order to come up with the model. Okay? In terms of implementation, you don't really have to do anything different apart from just loading a new model. Okay? It's called the rich regressors. Okay? Let me just show you that one real quick. So I'm going to do c3.ipynb. Okay? Okay, so first, same thing. I'm going to do utility functions right here. And then I'm going to load libraries. And as you can see that instead of loading the linear regression model, I'm loading called rich. So that's another class definition for it. The rest are the same. All the utility functions are the same. Okay. So let me make sure that I can run it. Okay. The next part is to usual loading the data, extracting the data, and also splitting the data. There you go. Okay, as usual, see, I want to experiment with the parameter, right? And I don't want to keep changing it, so I just write everything in here. So the parameter that we want to change is called alpha. So alpha is actually called the regularization strength. It's something right here, this one. Okay, so this one is called lambda, but I don't know why it's written as alpha in sklearn library. So it's the same thing. So when alpha is high, you are expecting smaller weights because it tries to cap the weight, so that the cost function for the weight is too high. So you can change your alpha in order to control how much you want to tame your model, essentially. Okay, so I go from 1 to a very, very high, to 1,000,000. And you can see what happened here. Okay. Again, what I'm doing is similar because I want to loop through all of my experiments, and then I'm declaring my model, and I'm expanding, I'm injecting different values of alphas in here, and then I'm training the model, all right, and then do the predictions, and then I'm doing the plotting. Okay. Okay, let me just run it for you. Okay. All right, so there are 4 models that are run in here. So the first one is when alpha equal to 1, and then 100, 10,000, and then 1 million. So the alpha goes up exponentially. As you can see that when alpha is to 1, it's actually the model is the same as the linear regression. It's pretty similar. So there's nothing changed at all. I mean, I guess a little bit changed, but the effects of regularization is quite small. But then if you can see that if you scroll down, this one might not see some difference. But if alpha is a bit too high, then it's actually flatten everything here. So flatten everything means that the weights, is, the intercept and the slope equal to 0. Okay? So, and as you can imagine that if you try to suppress the weight, then your R square is going to suffer, right? As you can see that alpha equal to 1, and then it gets lower until when alpha equal to 1 million. This one is pretty small, okay? Which kind of makes sense, right? Because you're trying to make your model not following the data, right? You try to make sure that the weights is not too high, okay? And you might be wondering, like, why would we do this, right? Why would we make a model such that your R square is low, okay? And the thing is depending on your data. If you know that your data is noisy and it can have some some strange value come into your data, then this is a way to kind of make sure that your model is robust against, like outliers and all the, all the like incorrect values and things like that. So, I would say that for your study, like when you're writing paper, you probably doesn't want something like this. But if you are like building the model for like production, like sometimes it's nice to have a model that can protect itself against outlier when the new data comes in. So that's kind of a situation that you might want to consider, maybe like ransack regressors and also something like rich regressions. Okay. Okay, so this is one way of making sure that your weights it's not going too high. There's another way that you can do is called lasso. Okay, lasso is it's another way of adjusting your cost function. So in rich regressions, you have W square. So that's the part where you want to I guess penalize the weights, right? Lasso is kind of similar, but different in a way that you are penalizing the weights by doing its absolute value. So it's a different mathematical function, right? I guess the difference that I can say is that it's favor something called sparsities. Okay, so it's very, very detailed. It depends on what you want. But lasso just actually will try to make certain weights in certain x go to 0. It's called sparsities. So depending on like the finer details of what you want to tame the weights, you might choose between lasso and rich. For me, I would suggest if that's come into the case where you want to do some regularization, I think rich is pretty good. I don't use this one as much, I guess. Okay, but it's certainly an option. Okay, let me show you what it is. Okay, so it's going to be this one, lasso. Okay, maybe I can just talk you through the code because it's the same thing. Okay, so again, I'm loading all the utility functions, right? And then, so this time, the library, the class definition is called lasso instead of rich or linear regressions. Again, same thing with the loading, extracting, and splitting the data. Okay. Again, I'm using alpha. So again, alpha is the strength of regularization. If alpha is too much, then your weight speed goes to 0, essentially. So I choose between 1, 10, 20, and 30. Because I know the range of alphas already beforehand, so I choose them accordingly, okay? And again, I'm just go through the same code because this is the same thing except for I change the name of the model from rich to lasso. Everything else the same. So let me just show you how it looks like. Okay, as you can imagine, alpha, when it's 1, then it means that there's nothing, you don't do anything much to your weight. But when alpha is increasing, that means you try to make the weights go lower So that means that you can see the slope is going to get smaller as the weight, as the alpha changes. This one is actually not that pronounced, but you can also increase the alpha value by yourself. We can try that too. But as you can see that the slope is kind of get lower and lower as the alpha increases. Maybe I can just do one more experiment when alpha is really high, just to show you. Okay, so I can do experiment 5 in here, and then I can make alpha like super high, maybe, I don't know, maybe 1000. Okay, so the nice thing about this is that I can just increase, like I can just come up with a new experiment by just writing it in here, and then when I run the whole thing, it automates through 5 iterations already automatically for me. So here, as alpha is equal to 100, right? You can see that it go to 0, right? So that's I guess you're suppressing weights too much, so that's not good, right? So maybe not too high, okay? And also, this is kind of nice to show this value, right? Because I was telling you that actually r squared goes from 0 to 1. So actually, that's not true. You can have also a situation where r squared is less than 0. You can have negative r squared. And what it means is that I think negative r squared means that your model is actually worse than straight line. If you were to just plot straight line in your graph, your model is worse than that. So negative r squared is even a no-no. Like that means that you're better off just predicting everything as the same value, the mean value. Okay, so that's negative r squared. Okay, so that's another way called lasso. Okay, and the last one is called elastic net. Okay, so this one is the combination of both. So as you can see that instead of using one or the other, why not use both? So we're using the contribution from the ridge and the contribution from the lasso, and then it's called elastic net, right? And in order to do that, you're going to have this value right here that you can control, like how much contribution you want from this term and how much you want from this term. I think it's still called alpha in your scikit-learn library, okay? So let me show you this one real quick. It's actually the same thing, only you're changing the things that you're loading from, okay? So I'm going to use elastic net, right? And loading the utility functions, the same thing. I'm loading the library, but now it's called elastic net instead of lasso or ridge, right? This one I'm loading the data as usual, and then here the thing, okay? So instead of using just one value to determine the strength of your regularization, there's 2 variables. So one is alpha, the one is L1 ratio, okay? So I always forget what it is, so I just write it in my comment. So if the ratio is 1, then we have lasso. If the ratio is 0, then we have ridge. So you can kind of see the ratio in here, okay, that you want, okay? Okay, sorry. So alpha is how strong your regularization is, but L1 ratio is how much you want your contribution from ridge or lasso. So I just keep it to be 2.5, 0.5, because I don't really have any preference between these two. So I just keep it both, like equal contribution from both, but then the strength is going to be different, okay? So again, I'm just running things in a loop so that I can run everything automatically. So I only change this one line, elastic net, and the rest are the same, okay? And when I run it, you can see kind of like the same effects. Okay. All right, so the result, again, the first one is when alpha equal to 1, 10, 20, and 30 accordingly. And as you can see that the graph, I guess the slope is getting smaller. And again, if I want to include one more example so that you can see that it's actually go to 0, then maybe I can go back here. I want to copy another exercise in here. And then number 5. And then maybe I can do alpha equal 100, and I'm going to rerun it. Okay, again, if my alpha is too high, then I guess my slope goes to 0, like this. as expected, okay? Okay, so feel free to play around if you want. Like maybe you can try changing the number, the values in here to see if it's changing anything. So all you need to do is to come up with a new experiment. Like you can even change the L1 ratio if you want. It doesn't really, it will run things automatically for you. Like I can change it to be 1, and then maybe change this back into 15. And then when I rerun the whole thing, then it will just run another experiment for me. Okay. And as you can see that your R square is going to suffer once you start to do regularization again. Okay. Okay, so in a way, what I've done here is that I want to show you that it's possible to do like this tricks in machine learning that's not available in your statistical process. So that's you know, I don't know, keep in mind, okay? Okay, so the last thing I want to show you for this topic is I want to show you how to do multiple linear regressions. And I want you to keep in mind that the best thing that we have, like the best metric, I guess the best model that we have right now is the linear regressions. The very first one, the simple linear regressions, which gives you about, let me see, the linear regressions. Give you something around like 0. For the trained data, I guess 0.5 each, right? And you're going to see that when you use multiple linear regression, you do have better model just by increasing the dimension of your data. Of course, right? Because you have more data, more things to fit to, then you do have a better model. Okay. Okay, so let's do that. Okay. So we'll do C6.ipynb. Okay. And here I'm going to go through the code a little bit more slowly because I want to show you that you do need to do standardization now. Okay. Okay, let me close everything I don't need. All right, so multiple linear regressions. The first code is the same, importing your utility functions. Okay. Okay, and the second one, I'm actually going to show you that we can use kind of like the same thing that we always did, but with multiple linear regressions. And I'm going to use linear regression. I'm going to simple linear. I guess I can use linear regression. Use rich, lasso, and elastic net. I'm going to use every model and just run things automatically. Okay. Oh, I need to rerun it, I guess. Okay. Okay, so the first thing is I'm going to load the data. So this one, same thing, the housing data, right? Okay, so this one I want to show you step by step. Okay. So the thing is that I want my data right here. So for now, I'm not going to choose, I'm not going to select kind of like the subset of my data. I want to use every column as my X, except for my Y column. So I need to use all of this, right? Okay. So if I want to use all of this, there are many ways for me to select the column, like all of this column. But essentially, if I were to do it straightforwardly, I want to do something like this, df, right? And you kind of have to type in the column name. For example, I want to choose CRIM, right? I want to choose, if I were to do this, I only get one column, right? If I want to do the second column, I use CN. So I have to type it here, in here, in the quotes. Okay, I get two columns, right? I want to have this one in dust, and I have to add it in here. Okay. So you can kind of see how painful this is, right? If I have to type all these columns in here, the name, like, and then in the future, if I were to maybe have one more column, then my code doesn't work anymore. So I want something that more scalable to different data, right? So what I want is that I want this thing in here. I want to generate these things in here, like this array right here. I want to generate it from the column itself. So that's the code that I had in here. Okay. So let's not do this. This one's too long. Okay. So first, I want to see what is the column. What are the column names in my data frame? What you can do is df.columns. Okay. So these are all the column names in here. Okay. So essentially, I do have access to the column names in a list already. But what I don't have right now is I don't have the one without my y, right? Because this one is all the x, right? Except for MEDV. So I want to get rid of this one. Okay, so that's what I want to do. Okay, so let me show the longer way. If you want to, if you want to get this one out, right? So you can do something like this. Okay. Okay, so I can do for, right? I in df.columns. Let me just show you that. Okay, and if I were to print I should be able to print everything, right? These are all the columns in here. Okay, so if I want I want all of this except for the MEDV. So maybe I can do something like this. I want columns to be an empty array, right? If my I, maybe I don't want it to be I want it to be COL because this is the column, right? So it makes more sense. So I want if my column is not equal, right, to the name MEDV, right? Actually, if it's not equal, then I want to store it. .append column. Okay, something like that. So that's what I want to. That's something that I want to do, right? I want to store everything in my columns array except the name MEDV. Okay, so if I were to print this one out, then you can see that my columns actually doesn't contain MEDV anymore. Okay, and then I can just simply use these columns right here in my data frame. I can do something like this, df, and then I just input the columns because that one is the array that contains all the x columns. There you go. And this is particularly nice because then I don't need to change my code if I were to include more x in the future. Like my data can have any x, any other x columns as long as my y is called MEDV. The code should be doing correctly, right? Okay, but you might notice that in my code it looks a little bit different. I don't write something like this in my code because I also use another trick. It's called list comprehension. So this one happen all the time. Like this kind of logic happen all the time when you start to doing like data processing and things like that. And then so there's another trick that you can do. It's kind of advanced, but I want to show you that it's possible if you want to wrap your head around it. Okay. So what I want is I want a list. Right. This list is going to contain something in it. Right. It's going to contain a column. Right? This column is going to come from the multiple things in it, and multiple things is here. Okay. Right. So let me show you this one first. Okay. So I'll just comment this out, right? And I'm going to say calls equal. If I were to do this, my columns actually going to contain all the names in here, including MEDV. Okay. So this part is actually saying that for all the columns in the column in the data frame, just put it into the list. That's called, it's almost like you are doing the for loop, but you're doing it in one line. It's called list comprehension, right? So that one's almost what we want, except for I don't want MEDV. So I can put another logic in here, right? If call is not equal to MEDV. Okay, and there you go. So one line. So I want to show you that this line in here is equivalent to the 4 lines on top, above. It's the same thing. It's the same logic, but it's shorter. And you might see something like this in the more advanced code. So that's why I'm presenting you right now, so that maybe you encounter, you don't get too confused what it is. But it's possible to do this whole logic in one line. Okay. And that's what it is. So once you get the columns, you're good to go, right? Because then you can do df.columns.values. Now you get numpy array that contains all the x. Okay. See, I could be overthinking this too, right? Like, you don't even need to do this. If you know iloc also can help you, okay? For example, I know that my df has a shape of 14 columns. And I know that my MEDV is the last column. Maybe another way you can do is you can do this one, iloc, right? And if you do iloc, that means that you have to think about the order. So I want the first 13 columns. So first I want all the rows. So this one, all the rows. And I want the first 13 columns. So it's 0 to 13. That one also works too, actually. Okay, so I could be overthinking this. But I mean, if you know that your data frames always have the y value in the last columns, then this one also works too. Okay, so there are many ways of, like picking the data in data frames, right? Okay, I digress. Okay, so my y, it's actually going to be the MEDV column. So y equal df MEDV dot values. So my y is actually just the one-dimensional array. That's all. Okay. Okay, so that's the only difficult part. As you can see that, like processing data is actually harder, more difficult than actually like doing the model building. Okay. Once you have the data, the rest is similar, like identical to what you always do. So I'm going to split the data. Okay, split the data in here. I need to run everything again to make sure. Nope, I haven't done this yet because, oh yeah, I need to set this to equal to x. Okay, right here. Okay, I got the train data and test data. Next step is called standardization. If you have many x, do not forget this. You won't get error, but your model will suffer for it. Okay. So standardization, same thing. Standard scalar, right? I'm going to set equal to sc, and then I'm going to do sc dot fit. Okay. So I don't know if you've seen this, but normally you would do fit and transform, but you can also do fit transform, because why writing two lines instead of one line? Okay. So set fit and transform x train, right? And this one is equal to x train standardized. And then this one going to be x test standardized equal sc dot transform. Okay. Again, notice that I don't do fit and transform on the second line. Okay, so this one is intentional. This one is correct. Like you might be tempting to do the same thing, right? You might be tempting to do fit and transform. That is incorrect. Remember, fitting we only fit to the data that we have. We treat the test data as the data from the future. So you cannot fit with the test data. You can only transform it. Okay, so remove that. Okay, so that's a little things that you can, I guess you can make mistakes on. So be take a notice on that. Okay, we're almost done. So the next thing is that I'm going to do model sets. Okay, so this one is a bit different in terms of how I set things up. Okay, so normally if I do one model, I have I can have a dictionary that's containing dictionary, right? But then when I do different models, it's a bit more complicated in a sense that I do need different class definition. So what I do is that I do something like this. So first I do an array. So let me just show you this one real quick. Okay. So first, my model set is an array. So let me just delete this one. Okay, it's an array. So so an array contains an item. So each item is a dictionary. Okay, and in each dictionary, there's always going to be two keys. The first key is called what is the model. Okay, and then this one I keep track of the class definition. So I want to do linear regressions. I do the one here. So notice that I don't do this one, because this one is the model instance, the object instance. I don't want this one just yet. I only want just the class definition. Okay, so that's something to note. Okay, so the next item in my dictionary is the parameter. So I do param. You can come up with any name, right? And this parameter is actually going to contain another dictionary, which has, the parameter that I want. For example, actually it's only contain one dictionary. For linear regression, there's no parameter, so that's fine. But then I can also come up with another model, right? Same thing. So it's going to be another dictionary with the key model. But this model is called rich. So that's the regularization linear regressions. But this one contains parameters, which is going to be alpha, right? So that's going to be the key, and the value is 0.1. Okay, so the way that you can, I guess this is the way that I came up with. Like you can do other ways. There's many ways to do this, right? But then I'm just showing you like how do I organize my experiments. And once you start to have more models that you want to work with, then you kind of have to keep track of, like the class definition too. That one needs to change too, in addition to the parameters. Okay. All right. So I'm going to copy this one from my code now. I want to show you how I kind of like organize my experiments. That's all. Okay. So as you can see that I have linear regression, rich, lasso, and elastic net. Okay. All right, so next stop is again, I want to loop through all of these experiments. So let me show you real quick. Okay, so I do model, sets, right? This one is actually an array. So I can do model for m in model sets. That's it. Okay, so that's different between when you loop the dictionary and when you loop through an array. So an array, you can just simply do for something in the array. And then I can also print m just to make sure that I have the right thing. As you can see that I can loop through the dictionary that contains the model definition, right? And then the parameter that I want. Okay, so for me, I want to use different things in here, right? So if I want to extract the model, I want to do this one, right? It's going to be m. And then I want to extract the model out. I can do model. Okay, because it's a dictionary, so I got to do this selection with the key value. right? So let me show you. If I were to print M and model, now I can have all this class definition, okay? So so I'm trying to show you that my code is actually not that cryptic, but I'm trying to make it concise, so that's why it's kind of hard to look at, right? So I have my model, but keep in mind that this model is only the class definition. If I want the object instance, I need to do the parenthesis, right? So I can do just that by just doing this. There you go. Like you can do this one. Okay, let me show you this. This one. This one might look strange. Like what is this, right? M model and then the parenthesis. But you have to go back into what I stored in here. What I stored in here is actually these instance. So it's essentially the same thing as what I'm doing, something like this. But I just change it into m.model so that I can change my model as I wish. Okay. So this part's okay, right? But then in here, this is the parameter that I want, right? I want the parameter to be expanded into here. Again, I want that dictionary that contains my parameter, and I want to star expand into it, right? So first, I want the dictionary, which is M, and then params. So M with the param is actually this thing right here, like all of this, which is in the, the value of the key param in here. But then I want to expand all of this inside my, my argument. So I have to do star. Okay. So essentially what I'm doing in here is that every time I loop through my model, I'm declaring, I instantiate my class definition, and then I inject all of this parameter into it. So hence, this really, really complicated, weird-looking syntax. But if you kind of go through like each of the pieces, it's actually the same thing as you just did before, but in a more, I don't know, concise way, I guess. It's one line, okay? Okay, so this is my model, okay? I'm gonna put it into my variable called MLR, so multiple linear regressions, okay? And as you can see that the rest is the same, right? I'm fitting the model, I'm plotting, storing the results, and putting to data frame. So let's do just that, okay? Okay, let's run the whole thing. Stop it. Okay. So what you're looking at is actually the, okay. So let me just not plotting residual for now, just to make sure. What is this? Okay, plot rest. Yeah, I wanna skip the residual for now. So let me just show you how it looks first. Oh, actually, you know what? There's no other way. Okay, so I forgot something that I want to emphasize. So notice that normally if you were to do like simple regression, you can actually see the data and you see the line through the data. But once you start to do multiple linear regression like this, when we have, I don't know, 13x, then there's no way to plot everything in one graph, right? So all you need, all you have in your disposal is actually the residual plot. That's the only thing that you have, right? So right now, you're looking at the residual plot from the model. And I don't know, convince me if you were to, I want to convince you, right? If you were to look at this, and if you look at the one that we had before from our linear regressions, I don't know, try convince yourself that the other one is actually better. Like this one is from 1x, and this one is for multiple x's, okay? The thing that makes this one better, there are two quantities that you want to look at. First, you can look at the magnitude, right? So this one actually go down really high, like into like -25. If you look at this one, then Yeah, it does have some, but in overall, it does look smaller. But this one is actually not that important because you're gonna see in your MSE anyway that MSE is smaller. But I want you to see that actually when you use multiple linear regressions, to me, I think it looks more random. There is less patterns in here, right, compared to this one. I think this one has more pattern, like it looks like this, okay? That's the thing that makes your model, I mean, that's kind of like the definition that of like if your model is better or not, that's kind of exhibited through the residual plot, okay? So less pattern, okay? And again, you can kind of see also through the value of R squared, right? Now we get something like 0.67. I think if I recall for a simple linear regression, we have like 0.5. So we do improve the model by just including more x, which I guess makes sense, right? Okay, and again, you can also see that if I do rich and lasso and elastic net, then we do have slightly decrease in R squared and also, I guess, increase in MSE. But that's just because we don't fit everything perfectly. We try to make the model more robust, and then in the, I guess the trade-off for that is that to actually fit worse. But it's guaranteed, I guess it's a safer model for the future in production. Okay.